So in this lecture, we'll look at acceleration in Cartesian and polar coordinate. Okay. So let me remind you, what was velocity in Cartesian coordinate? That is in basis state I cap and j cap. So we learned that velocity was x dot along I cap and y dot along j cap. This was velocity in Cartesian. Then what is acceleration? We know that acceleration in Cartesian coordinate will be just time derivative of velocity. Okay, so let's draw the diagram. This is our y-axis, this is our x-axis. Okay, so this I represent as I cap and this I can represent it as j cap. This is my point P here. Okay, let me draw a radius vector from here to point P. That. So this is my radius vector from origin O to point P. Now look at something interesting here. As this point P moves along a particular path with time, so say the point, let's do it in this way. So here the particle was at time t equals to 0. Okay, t equals 0. Now as the particle moves, the particle moves with time, so let the motion of the particle be something like this. So you can see that in Cartesian coordinate system, each point can be represented in terms of I cap and j cap. That is, the basis states are not changing with respect to the positions and also with respect to time. Okay, so what I can do is I can easily write dv by dt as, keeping in mind that I cap and j cap are constant, so the derivative only acts on the coordinate. So x double dot along I cap, and this becomes y double dot along j cap. But when you go to polar system, something amazing happens. Remember, in polar system, what do we use? We use basis vectors or basis states r cap and theta cap. How did you write velocity? You wrote velocity as v equals r theta r cap plus r theta dot theta cap. Okay, let me remind you something very important here. The radius vector in polar coordinate was given as magnitude of r into r cap. But when we were asked to find the velocity, we had to do the time derivative of r vector. That is, we had to do the time derivative on magnitude of r and r cap. And what we did is we acted this time derivative not only on the magnitude of r, and we wrote the first term as time derivative of magnitude of r into r cap, but we also acted the time derivative on the basis state itself. That is, we did d r cap divided by dt. So in the first case, we say that the basis states are not changing with time, but in the second case, we see that the basis states are changing with time, so we have expressions dr cap by dt. what the hell does this mean? Let's try to understand. If you look at the motion of point P, when the point P was at time t equals to 0, the direction of r cap was like this. But if you look the point P after certain amount of time, say you look at point P here, okay? So after certain amount of time, P is now at this point. Then you look at carefully, the direction of r cap is different. It means that r cap is a basis state of the polar coordinate which is not fixed. It somehow depends on the position vector. Okay. Similarly, if you look at one more position of the point P, look at here at this point. Okay. So when you look at this point, what do you see here? At this point, the direction of r cap is different. Let me call it r double dash cap. So it is quite clear that in the polar system, the r cap is changing with position. And we know that theta cap is perpendicular to r cap. So if r cap is changing, then quite naturally theta cap is also going to change. Okay. Why I said theta cap is also going to change with time? Because when we will find acceleration from this term, we have to act our time derivative not only on r dot and theta dot, but the time derivative will also act on r cap, and the time derivative will also act on theta cap. That's the weird thing. But now we understand why the weird thing is so. Because the basis states r cap and theta cap, or the basis vectors in this polar coordinate system, are changing, okay, with respect to the positions of the particle. So let's write acceleration. So acceleration equals to time derivative of velocity. Okay, so what you need to do is you need to have the time derivative act on r dot r cap plus r theta dot theta cap. Okay, it's going to be a long term. Let's write it. So it will act on the first term, giving us r double dot into r cap, and then we are going to have r dot into r cap dot. Okay, then the second term, for you'll get r dot theta cap. Then the derivative will act on theta dot, so r theta double dot theta cap, and now the derivative will act on theta cap, so we have r theta dot theta cap dot. So we have so many equations here, so many terms here, with some terms which we don't know, we need to find out. For example, we learned that dr divided by d theta. We found this expression dr cap, actually dr cap divided by d theta was turned out to be theta cap. Okay, let me remind you what was r cap. We have seen r cap was written as cos theta I plus sine theta j. And what was our theta cap? Theta cap was found out to be minus sine theta I plus cos theta j. But we have to find one more term. What is d theta dot what is d theta cap divided by d theta? Use this expression and you will find this is equals to minus r cap. Okay, so we are going to use all these expressions right now. So look at this expression carefully. From this expression we can easily find what is d r cap divided by dt. Okay, I'm doing it again. So this one you can write it as d r cap. Now r cap is a function of theta, so bring a d theta here, and theta is a function of time because as the object is moving theta is changing with time. So this is what? Theta dot. So d theta by dt is theta dot, and d r cap by theta is theta cap. So if you see r cap dot, then instead of r cap dot, what you can write? Theta dot r theta dot theta cap. So what do you see r cap dot here? So in terms like here, you're going to replace it in this way. How about this? What happens to time derivative of theta cap? So time derivative of theta cap will be found out to be minus theta dot into r cap. So this is my theta cap dot. So let's see, where does my theta cap dot comes? Here. Okay, so in this way, in the acceleration term, you need to make the following replacement, and after this you get this following expression, which is very easy. So acceleration will be in the end found out to be r double dot minus r theta dot square in brackets. So these are the terms with the basis vector r cap, and let us see what coefficients the basis vector theta cap has. It contains r theta double dot plus 2 r dot theta dot into theta cap. You see, now the acceleration has been written in terms of r cap and theta cap. This is what we want. We wanted that this acceleration to be expressed in polar system. So in polar coordinate system, you need to use the basis vectors r cap and theta cap, and this is the expression that you get. Okay.